Welcome to my talk on application solutions for machine learning vulnerabilities. Today we will look at the convergence of machine learning and web application vulnerabilities, and we will pinpoint existing vulnerabilities in the threat landscape that grows larger day by day. Before we jump into these machine learning related application security questions, here's a bit about me. My name is Maria, and I'm a security researcher and PhD graduate student at Dartmouth College in the United States. A few of my research interests include binary analysis, specifically exploring graph theory, machine learning, and supply chain related security. So this talk is about machine learning vulnerabilities. From my observations, I've noticed that machine learning vulnerabilities resemble those of web application vulnerabilities, almost as if they are a subset. I will get into this idea in a few moments, but here are a few well-known machine learning vulnerabilities that I will go down, or threats presently exploited in our systems. The first example I have listed is data poisoning, which I have studied the most in my past personal projects. In this case, malicious training data is injected into a model to change the model's intended behavior. Next up, we have prompt injection, perhaps one of the more well-known machine learning vulnerabilities. Prompt injection involves crafting input that embeds instructions or hidden data to manipulate an LLM into performing unintended actions or revealing sensitive information. For model inversion, an attacker would use model outputs to reconstruct sensitive features or inputs used during training. And similarly, for model extraction, the attacker would reconstruct an entire model's functionality or inputs. Finally, supply chain attacks are a familiar vulnerability involving compromised libraries, pre-trained models, or tooling that introduces hidden weaknesses into otherwise trusted machine learning systems. Intuitively, all these vulnerabilities, even if we are not familiar with machine learning, resemble web application vulnerabilities. And machine learning is being explored more and more, not just in the tech space, but also in the security space. So, like, how can we exploit LLMs through supply chain attacks? How can we cause Gen AI models to output unintended results? For the past 25 years, web application security has been dominated by assumptions regarding the input supplied by web app users. We were building systems that assumed users would behave in a certain contextual way, and attackers exploited that assumption, and that's why we have a whole offensive security industry dedicated to not just web apps, but other domains as well. And these are a few simple parallels that I've noticed, and a lot of vulnerabilities encompass some type of user-supplied data input generation. For instance, SQL injection attacks are akin to prompt injections instead of crafting malicious SQL. Attackers craft malicious prompts to manipulate AI outputs. Cross-site scripting evolves into model inversion attacks, where instead of stealing data through script injection, you can extract training data by querying the model. And supply chain attacks almost draw parallels to CSRF, where outside reliant technologies are manipulated and referenced. What I want to convey is that machine learning vulnerabilities follow the patterns of existing web application vulnerabilities, with the common trend being user-supplied data input. But despite these similarities, existing tools fall short. We cannot use the same tools for machine learning vulnerabilities as we do for web applications. Web apps are deterministic, same input, same output, but machine learning models are probabilistic, making vulnerabilities harder to reproduce and test. There is a clear attack path vector and path from web applications, while there could be billions of potential generated outputs from machine learning models. This is like a very simplistic take, but in cases of LLMs, we have already begun to see this happen. For example, poisoning attacks can compromise models of various model and dataset sizes, even if the largest model is trained on 20 times more clean data. So there's a larger proportion of clean data to bad data. This paper shows that inserting as few as 250 malicious documents into the training set can create some kind of backdoor in a language model, and that this vulnerability scales independently of model size. So in other words, even large models are just as susceptible as smaller ones. What this tells us is the volatility of LLMs. Essentially, with a relatively low amount of poison, we can compromise such a model. But we do have a need to use these machine learning applications. We do want to safely use LLMs, which means we need to trust them. What we want to know is how can we increase awareness with regards to machine learning models and how they are made. But our existing tools do not always satisfy these security practices. Beyond our tools, there's a certain mismatch towards web application tools. Most existing tools are designed for traditional software, as in they look for code vulnerabilities, configuration errors, and network intrusions. But machine learning vulnerabilities often live in data and model weights rather than in code. You can't scan a neural network for vulnerabilities in the same way you would look for low-hanging fruit in a penetration test. There's also a certain problem with regards to detection in traditional security tools. We use pattern matching for known patterns, but just as you saw in that Anthropic paper, you can poison a model with as few as 250 documents out of billions. This would be about 0.00016% of the training data. Our current data filtering tools are just not powerful enough for these sparser attacks when on the surface level the poison content looks normal. And to add on to all of that, any current solution we have often has performance catches, like adversarial training taking too much time, formal verification being computationally intractable, or differential privacy degrading the quality of model output. But the overarching problem of machine learning vulnerabilities is scale and speed. These models evolve, and jailbreaks evolve faster than tools are often being built in real time. And we can't even explain the anomalies that we find. So oftentimes, even if we do find something, we don't know how to fix it. The bottom line is we try to secure these systems that we do not fully understand, but let's not lose hope. There are a few hopeful solutions for understanding and analyzing machine learning vulnerabilities at a technical level. First, to get it out of the way, there is mechanistic interpretability, which is essentially reverse engineering for neural networks. It's a topic that I'm currently interested in researching further and would hope to do so alongside the community. However, there is not much theoretical foundation to it as of yet. In a related way, program analysis has had a lot of interesting recent developments. Problems are more structured, and programming language-related frameworks exist and are being developed. At its core, code has semantics that we can understand intuitively. Unlike some machine learning research that is purely theoretical, program analysis can help us find some real, more practical bugs. In terms of what we look at today, I've prepared a few demos of bugs and solutions in the machine learning vulnerability landscape. We'll go through these sequentially and discuss solutions to these problems, after which we will conclude. So there has been a lot of research into the vulnerabilities found in machine learning code bases. Oftentimes, these are issues that are overlooked in favor of deploying these models faster. Perhaps most famously, Python's pickle library is used to load untrusted data. Pickle can execute arbitrary code during deserialization, making it trivial for attackers to achieve RCE. Despite this being well known, many machine learning projects still use model weights, datasets, or pre-processed features using pickle.load without validation. For context, what is Python's pickle library? Pickle is Python's native serialization format that can serialize almost any Python object, not just data, but also code. When you unpickle an object, Python will execute objects embedded in the pickle stream, which makes it remotely executable. For this reason, machine learning code bases that pickle intermediate results are particularly vulnerable, and present some interesting complications that can involve poisoning model weights that can be interesting to observe as well. So in this short Python script, I wanted to demonstrate a simplified pickle exploit, where you can see how simple it is to deploy a remote script that exploits a user's system through the usage of their pickle library. Initially, we import the necessary packages. Next, we create a really basic exploit for ourselves, invoking the reduce function that tells pickle how to serialize an object. By returning a callable and its arguments, you can make pickle execute anything during deserialization. The highlighted function will execute when unpickled. In the last two lines, you have a crafted payload, and the last line represents the victim loading said malicious pickle. This is a simple attack for demonstration purposes, but more complicated attacks can include consequences such as establishing reverse shells, exfiltrating data, or backdoors. So Pickle is a fantastic and convenient module, to be honest, that works really quickly compared to safer alternatives. With this being said, there are absolutely alternative mitigations to using Pickle. First, safer serialization formats exist, such as safe tensors and safer binary formats. Safe tensors is a file format for storing large tensor data that prioritizes security, efficiency, and portability. Safe tensors works as a format since it consists of a JSON header describing the tensors that include things like name, shapes, data types, and then a byte buffer that contains the actual tensor. Basically, only the data is accessed and the malicious code is not executed. Similarly, binary formats are also used to serialize data rather than executing code. Beyond these two solutions, there are a few others such as sandboxing or isolating loading pickles in containers or virtual machines. And then there is also cryptographic signing, where models may be signed with keys and verified before loading, similar to fingerprinting. Although the machine learning world is moving away from using Pickle, if you must use Pickle, then treat it like you would a binary executable, because that's essentially what you're doing to load in the data. Now I want to go into some data poisoning, specifically poisoning of the MNIST dataset. Data poisoning is a very well-known machine learning vulnerability that takes a model's training data and manipulates it in order to achieve a new undesirable outcome in a model. Manipulating or poisoning the training data may mean addition, modification, or deletion of data. The goal of an attacker is to influence the model's learned parameters by controlling some portion of the training data. I want to reiterate, just like the earlier paper I mentioned, even a small percentage of poisoned samples can significantly degrade performance or introduce specific vulnerabilities. It is such a small percentage that even 5 to 10% is enough poison to create backdoors in most models. So for our purposes today, we will be poisoning the MNIST dataset, which is a standard binary classification. Is this the correct number training data set? This data set has an error rate of just 0.8%, which is why it is nice to experiment with in terms of data poisoning. I prepared a video demo of poisoning the MNIST data set, forcing the model to misclassify 1s as 2s and then 2s as 4s. So I coded this in Jupyter Notebooks for demonstration purposes. So MNIST is a bit like the hello world of machine learning. It's a very basic data set that people use for experimentation, as have I. So here we are training the initial set. And here is where we begin to poison. So right here, in this for loop, we poison the 1s into 2s, very, very simply. And then we just poison 10. So not much of an impact just yet, but as I said earlier, it only takes a small amount to poison a data set. Then we retrain the model. And then this time, we poison 30. And you can kind of see the percentage correct, which is not entirely accurate in definitionally in terms of percentage, kind of changes from 1s to 2s. And it changes almost equally, so the difference is almost equal. But again, there is that error rate that affects how it's processed. Then we always have to go back and retrain the model. And then right here, we're poisoning 100, which is much more significant since our total number is 1,000 for I in range 1,000. So this is 10% of the data set that is being poisoned. And here, I wanted to poison everything. So I wanted to poison 2s into 4s. And so this will be a lot more significant. So the difference is much more drastic between 2s, which is 50% correct, and 4s, which is a bit of an anomaly with 146% correct. And then here I have 1s into 4s to demonstrate the same result. And here's my final training. So the MNIST poisoning attack I just demoed is actually quite simple in the grand scheme of things. I listed here a few attacks that increase the complexity of what we can do with data poisoning. For example, we can have more targeted backdoor attacks that inject samples that cause the model to misclassify specific inputs while maintaining a good overall accuracy. This is more sophisticated and has several applications, such as computer vision misclassifications, where a computer may be unable to determine what should be safe or censored by pixels. There's also the famous autonomous vehicle from the cited Badnets paper that discusses poisoning, where a car may misclassify a stop sign based on the existence of a small sticky note covering it. Finally, I wanted to mention label flipping attacks, which are another form of data poisoning, but this time misclassifying the labels or weights of the model rather than the additional sophistication of the backdoor attacks. Overall, data poisoning is a real threat to data sets in any part of the software supply chain that involves training data. The best mitigation for data poisoning is strictly tracking data provenance. Data provenance is the history of a particular data set, including its creation and transformation over time. There are existent tools that supplement this quite strongly, but the main goal is to track fingerprints at certain times to have a clear picture of the data set as it changes over time. To add to data provenance, anomaly detection is also something to consider when looking to mitigate data poisoning. Anomaly detection is the task of identifying data points and observations that deviate significantly from the norm or expected behavior. So when you saw those percentages that went over 100, which didn't make any sense, that would be an example of an anomaly. Here I have a really simplified standard deviation detection script that would be used for this purpose for anomaly detection. Ultimately, when creating and training such data sets, developers should maintain the assumption that data might be poisoned and designed accordingly, since data poisoning is difficult to detect and easy to poison once a way is found in. Finally, moving on to model extraction. When we consider machine learning models, we have to remember that they are intellectual property with proprietary training data and engineered effort and training. Model extraction is an attack where an attacker with only black box access to a model, meaning they can only query and see predictions, reconstruct or reverse engineer a functional equivalent of the model. They only just need the ability to send inputs and receive outputs. Such a data leak invokes a theft of the model itself or intellectual property. It is an intuitive approximation of the model's architecture, so we will follow this illicit attack pattern in my demo. So here, again, this is not the MNIST data set. We're training a synthetic data set. So you can imagine that the model is just the victim's intellectual property model. And we have an attacker that would query this model and collect these responses. This is typically done using some API. So now we are training our stolen model on 100 query responses. And then we, as attackers, want to reevaluate the success of this extraction. So we make some statistics. We analyze how accurate the model is, our model is, versus the victim's model. And now we can visualize decision boundaries and look at additional statistics and graphs to take a look at the difference. But similarly to attackers, as defenders, we also want to look at these things statistically. When triaging a model, we also want to compare a stolen model to the victim's model to compare how similar it is to our intellectual property. So these are some additional statistics, and we're looking at the query efficiency. I think that model extraction is an interesting vulnerability because one is almost intuitively extracting and reversing a model from fairly simple queries. But in my opinion, the real threat is the information that model extraction can imply. Besides intellectual property theft, you have theft of potential personal information, depending on the model and what information it trains on or carries. A lot of the mitigations that I want to talk about rely on optimizing the model's prediction capabilities, but they come with heavy trade-offs such as quantization, which returns less information regarding prediction or queries, but you will also have less valuable predictions as a result. So, and also perturbation comes with output noise, which may hurt users' confidence in terms of the model. Rate limiting, as we know, comes with the trade-off of hurting the legitimate user through limiting query quantities that we can run. Finally, listed here, I have fingerprinting, which embeds a signature into the model that can prove ownership if stolen. Although this method is pretty effective, it is not preventative, but rather reactive in situations like IP theft and legal disputes. Ultimately, I think that the best prevention measure is using a combination of mitigations, as in every scenario, as well as regular security audits to reinforce the defenses that we currently have. When it comes to machine learning models, we want to be able to use the models effectively. And using such models effectively means being able to trust such models. When we, as average users, use such models, there is an implicit trust in the model's intention that it will, 1, provide predictive capabilities, and 2, be implicitly safe to use. This is different than what we initially think about web applications because the line is blurred when it comes to machine learning models. An attacker can use a model perfectly legitimately and still query it to extract it, as we just saw. Oftentimes, the predictions from the model itself can become leaks implicitly or explicitly. And trust is not binary the way that it is in web applications. I wanted to show you that the percentage of a model's informative accuracy changes over time, but with web applications, it is a matter of whether a user is trusted or not. Ultimately, what I want to conclude with is that security fundamentals don't change. Inputs should be validated, and users cannot be so easily trusted. Guided by these specific principles, we can adopt these principles and learn from web application security, applying that same knowledge and principles to machine learning vulnerabilities. Sure, machine learning models are probabilistic versus determined web application models, but this is just a new problem and perspective to wrestle with that we can understand through our past patterns. Users can also be given the least privilege access in machine learning models that they are given in web applications. An application in both scenarios should return the minimal information needed to serve the user. Threat detection is also something that can be implemented in both web application and in securing our machine learning models, which means in this case detecting unusual query patterns. Beyond threat detection, we can continue the integral parts of the security ecosystem that include incident response and security audits, which are commonplace. Having recovery procedures in place in case a model is stolen as intellectual property, for example, is imperative in case incidents happen, which they have and will. I also list formal verification here. Although it is computationally intractable, we can analyze models to prove that they operate securely and correctly under defined conditions. Finally, it's cliche, but we have to embody the attacker and realize these problems and scenarios before more intentionally malicious actors discover them for us. The attacker is actively creative and will exploit not just known vulnerabilities, but the unexpected gaps in our existing defenses. All of these points apply to web applications as well as fundamentally to machine learning applications. Intuitively, we can recognize the same weaknesses shared between new applications that integrate some kind of machine learning into their framework, which has become so commonplace. We see trust evolve from being binary, true or false, to becoming a hazy relationship between the user and a model. This new relationship is exploitable, but ultimately it means we have infinite possibilities to creatively evolve our defenses and mitigations. Thank you.